Afternoon, everyone. As David said, today I'm going to talk about the Beaulieu Park Station project, and David currently gave an introduction of what I'm going to discuss. So I will not repeat this. I'm going to just pass through a brief, firstly, introduction of myself. I'm a principal engineer in rail mobility and infrastructure asset management in Arcadis, UK. I'm leading the trackbed discipline nationally and also in international projects. I'm a chartered engineer with the Institution of Civil Engineers and the Permanent Way Institution. I have spent a significant amount of years in track innovation and research and development, providing specialist guidance on track performance analysis by both analytical and numerical modeling and by track instrumentation. Well, currently I'm more focused and spending more time in design and engineering for track renewals, enhancement schemes, and multidisciplinary projects, while in parallel I provide technical advisory for asset management in Arcadis. In Arcadis as well, I would like to say that apart from the in-house trackbed design and geotechnical design and modeling capabilities, we have as well in-house trackbed investigation facilities. And while in parallel, we use a wide variety of digital tools and automation tools, and we have an established innovative supply chain partnering. So Beaulieu Park Station. This, by the way, is the first railway station to be built on the Great Eastern Main Line for over 100 years. So Arcadis was appointed by John Murphy and Sons to provide among the multidisciplinary services, so all programming, constructability, OLE, track, drainage, civil, earthwork, geotech, everything, the trackbed design as well for the Beaulieu Park Station development, which is located to the northeast of the Chelmsford, Essex. The project is in the LTN1 ELR, and it is approximately 3 miles northeast of Chelmsford. The new station is part of a wider development, which includes construction of up to 14,000 new homes, a new public highway junction connection, demolition of a bridge, and replacement with a new overbridge. The scheme consists of greenfield station development with 3 new platforms, a new station building, new car park, and new taxi bus terminals. To serve the new 2 platforms, the existing down and up main lines will need to be realigned, and a station loop line will need to be introduced. The elevation as well, like the topography of the current site, is varies between 40 meters and 28 meters. So we have a change of elevation of 12 meters approximately. You can see the location here on the map, approximately where the station will be back, and the whole thing will cover the whole alignment, new alignment. As you can see here, the existing up and down main lines where it's located. This is a proposed speed diagram of the proposed works. So this provides the general extent of the full scheme between Chelmsford and the proposed station and Brickhouse crossovers to Colchester. The project included the introduction of an additional loop line, as I said here, between the down and up the proposed up and down lines, and necessitating the widening of the existing railway corridor between the overbridge Whitehart Lane Bridge 160 to the south mileage and Boreham Viaduct to the north mileage of approximately 2 kilometers length. The project included the introduction of 3 platforms of approximately 250 meters length each. So platform 1 and 2 served to be served by the up main and loop lines, and platform 3 served by the down main line, as you can see in the speed diagram here. As well, there are 2 proposed footbridges and access for all overbridges, providing access to platforms 1 and 2, and a secondary means of escape overbridge on the countryside edge of the platforms. A wider rail corridor is is required to include the additional loop line and the realignment of the down main, the new down main line. The lines are bidirectional. Um, a railway boundary change and embankment widening work is required. A new oil is required. Proposed roll rate access points between the semi-B bridge and the higher mileage crossover is required. New trackbed formation treatment, new drainage network with under-track crossings connecting to the nearest outfall. Here, as you can see, it requires installation of both plain line, track, and SNCs in the whole extent of the size. Sen 60 rail will be used. G44 sleepers will be used with under-sleeper pants. Proposed line speed is up to 100 miles per hour and track category 1. And as well, speed tonnage increase is proposed from 31 to 42 million gross tons per annum. The actual trackbed design, as you can see in all the red lines here, includes slewing of the up main and realignment actually of significant part of the up main line, removal of existing switches, speed increase, traffic increase, and the actual new trackbed construction for the 3 lines, for the up main, the down main, and the loop main line, that is approximately almost 4.5 kilometers in total. And now passing to the trackbed design standards that are mainly used. So the trackbed design was based mainly in the principles as they stated in these standards. So the basic one is the 4239 standard, the trackbed investigation design and installation standard, the design and construction of track, the network rail to TRK 2102, but as well a lot of clauses as well were utilized from the environmental standard and the 177 monitoring of track standard. Which are the basic trackbed design principles applied? As you can see, these are the main graphs and plots from the 4239 trackbed standard of network rail. That give specifications about the dynamic sleeper support stiffness, kilonewton per millimeter per sleeper end, in comparison with the geotechnical parameters. And so actually the proposed track category and proposed speed were taken into account. The minimum required K value dynamic sleeper support stiffness was taken into account for plain line and SNC sections. The minimum ballast thickness had to be established. The total thickness of granular trackbed layer had to be determined based on the parametric or of the geotechnical parameters of the substructure layers. Use of geosynthetics was used. This means different types of geosynthetics. And then in the embankment as well, because two of the lines, some part of the 2 lines of the down main and loop main was to sit on the virgin ground with embankment fill. That means that target values for deformation modulus had to be established as well for this area. And of course, some efficiency and value engineering had to be applied because there were areas of track lifts and track lowering and slewing that was existing footprint versus the areas of greenfield areas. So to limit the required trackbed thickness where appropriate. The main trackbed design methodology applied during the design stages is the following. Firstly, a desk study was conducted to identify the geological background conditions of the whole extent of the site, to assess any previous ground and trackbed investigation reports. Then the following step is the specification and the production of a trackbed and ground investigation scope that would fit to the final design. In parallel, this was in parallel as well with the specification of the particular and special geotechnical and geoenvironmental and contamination testing specifications. Then the actual trackbed investigation and ground investigation and lab testing took place. And this led to the final trackbed design, analysis, and process. and the production of the detailed design. And we must say here that during this phase, during this stage, close collaboration between the trackbed team and mainly the track P-way team, but as well with the drainage, geotech, and civil disciplines was required. Now, let's split it now all these to one by one, starting with the geological background of the project. The local geology comprises superficial deposits of high deposits of sand and gravel with lessons of clay and silt. Glacial deposits are also noted and were shown to comprise glacial sands and gravels, with clay and silts lying to the south and north outside the main station development area. The solid bedrock geology on site was London clay formation and was noted to comprise an bioturbated and poorly laminated silty clay with some layers of sandy clay. For the areas of the existing trackbed corridors that had to be examined due to slewing or realignment, the standard deviation of the vertical and horizontal alignment for each eighth of the track sections of the existing down main and the existing up main were examined. Track quality indicators as well were examined, were taken into account, were appropriate. But in all remaining areas that fall out of existing pulpit that are in greenfield area actually, trackbed design was governed by the geotechnical and ground investigation results and the proposed tonnage and speed. Now looking at the trackbed investigation, so for the existing track corridors, a great variety, a large volume of automatic ballast samples and trial pits were carried out. The condition of the ballast layer was dirty, with the sub-ballast layers comprised of granular and cohesive layers of sand and gravels with pockets of coarse silt in clay, sand and gravels, and the underlying subgrade was soft clay with areas of firm clay. In the greenfield area of the proposed two lines, down and loop, there were a lot of GI that were analyzed. Some of them as well were conducted during grip 2 and 3, but the very additional ones were carried out during grip 5 detailed design. This included additional window samples, trial pits, and cable percussive boreholes. And the result of this was analyzed, as you can see, in digital formats and in long sections, and ground models were developed. This was as an average, it was a mixture. The ground was a mixture of made ground, firm to stiff clays, with local pockets of soft clay present and smaller areas of loose to medium dense sands and gravels. As well, apart from during as well, this as well, geo-environmental assessment and ballast contamination for disposal purposes was carried out by Arcadis as well. The groundwater levels were examined and the existing track drainage was examined to inform as well the drainage for the proposed alignment. The existing, here you can see as well part of the proposed alignment. So the green lines are the existing up and down, and you can see realignment of the up towards the south, and then the new proposed two lines, loop and down main. This is part of the alignment. So the new, in high level, the new trackbed included 300 millimeter of ballast in the majority of the site, geotextile separator, geosynthetics, geogrids, and geocells. So in this project, the application of geocell was applied, it was used, filled with granular material at varying depths. So here you can see some typical cross sections for the two proposed lines, the proposed up main, the down loop and down main. Here is the embankment widening area, part of some at one channel. The As I said, in a significant part in the platforms area around there was embankment widening requirements for the down main and loop main, where the trackbed had to be constructed on top of the embankment fill, and specific targets were set for the deformation modulus. Outside the embankment widening, the trackbed was constructed at grade or within a cutting. Of course, in all areas, efficient drainage was applied, and the trackbed had to follow the crossfalls for the discharge of the water. As well, the design included the specific requirements and specifications for compaction, formation testing, and track monitoring after construction. As I said, and as you can see, as you saw in the cross sections, to provide a more sustainable solution that requires less material excavation, the use of geocell was implemented in the trackbed design of this project. As you may know, geocells are an expandable honeycomb panel, commonly made from HDPE, high-density polyethylene or geotextile fabrics. And this panel is filled with granular material to create a more resilient formation layer that can better distribute the vertical stresses generated by the train vehicles to the subgrade. The use of geocells has various advantages and disadvantages over more conventional trackbed construction, because it leads to load spreading improvement. It reduces the track deflections. It leads to increased track modulus and to reduce track settlement, long-term track settlement, and ultimately to reduced vertical stresses on the subgrade. The use of geocells leads actually then as a result to stiffness and bearing capacity improvement, and this is achieved through three main functions of the geocells: the vertical confinement that is generated from the infill material friction with the walls of geocells, through the lateral confinement function that is generated due to the geocell mattress ability to limit the upward and lateral movement inside the cells, and the tension membrane effect that is due to the vertical applied loads and the resulting tension in the geocell's wall. Unlike the two previous effects, this normally takes place when the geocells start to develop significant vertical deflection. As you can see here, the conventional depth of construction versus trackbed construction depth using geocells. Specific guidance had to be provided to the contractor regarding the installation of geocells layers, as you can see photos of the project. So for example, the geocell infill material should be clean granular material with a maximum particle size distribution. As well, the guide here, the Eastern Regional Track Guidance Note was applied for the granular material specification. As well, guidance was given regarding the installation of the geocell panels and the connection from each panel to the other, the ordering fill regarding the compaction requirements, and as well regarding the procurement, purchase of only Network Rail approved products. Specific, as well as you can see in the photo, is that the design included the application of geotextile separators both on top and on bottom of the geocell layer. And this is a geotextile separator is required on top of the geocell layer to prevent intermixing between the granular infill of the geocells and the ballast. And at the bottom of the geocell layer, the geotextile separator is recommended in order to prevent the bottom, to prevent any potential loss of granular fill through the bottom of the cells that could occur due to the intermixing with the subgrade material or washouts. Now, what was passing on some of the design challenges. The proposed permanent way was to be constructed under a combination of ALO, all lines open, and possession blockade construction access. And the proposed track infrastructure comprises plain line combined with numerous SNC units. All proposed and all the works are tying into the existing track geometry at the extremities of the work site. So now, due to the large volume of works, it was intended that some of the construction elements, some of the trackbed, for example, and track all works, to be conducted not only in the December and Christmas blockades, but to be risked and to be undertaken, but to be undertaken in other timings in advance of the final blockade. But this created a lot of challenges, especially with the trackbed construction, because the existing plain line geometry would need to be reinstated with a temporary to allow the operation of the trains while the construction of the project. And the proportion of the trackbed formation that is new and does not interfere with the support zone of the existing alignment can be constructed offline in accordance with the design specs. So you will understand what I mean in the later focus. So to make it more simple, what it means, this project had some complexity because it had to be delivered in multiple stages. So as you can see, stage 1, it included only the SNCs here, realignment of SNCs and the formation treatment of these SNCs, the permanent formation treatment of these areas, and some civil earth widening as well. The stage 1 included in green zone work, so ALO, it's this widening area, included the construction of down main and loop lines and the points, these points either side, including all the formation, treatment, and drainage of these areas. As well, this stage, the partially included the foundation of the 2 footbridges. Following stage 2, included now the connection works. This was during Christmas blockade 23-24 in London and country end to act as operation lines while keeping now the up main and platform 1 under construction, so free for under construction. The final down main and loop lines and the points are now clipped out of use to isolate the up main during its construction. The up main is here to be realigned. The following stage is the up main and drain. It's now actually the construction of the up main, the proposed up main and the proposed drainage installation in green zone worksite, and as well the completion of the 2 footbridges foundations and other ancillary civil works. Finally, the final stage is the final commissioning stage, which will connect all the track gaps, all the platform coppers will be installed, including removal of the clips of the 2 points that will connect on lines and leave trains to operate and run. So what does it mean for trackbed? As you understand, keeping some lines open and constructing in close proximity the proposed or temporary lines created a very needed and required a very detailed program and design deliverable. So areas among that there was areas where there was increased track lowering. In some areas were more than 0.6 meters below existing levels. And there was a lot of areas where excavation works were adjacent to the track support zone of the existing running lines. And in order to maintain the current alignment after installation of the proposed permanent trackbed, a temporary trackbed solution should be applied, should be installed. The temporary trackbed would be constructed on top of the final trackbed layer, that in this case, the final permanent layer, GSL layers for the final alignment position was installed first, and then maybe additional ballast layer was required to fit the temporary alignment. New ballast, for example, for the temporary trackbed should be compacted as well appropriately for a safe operation of the temporary running of lines. And as well, where appropriate, old excavated ballast could be used for the cess and ballast shoulder purposes. So here you can see in purple in this photo the final alignment position here, for example, SNC, while in blue here and red is a temporary alignment with increased ballast thickness for the use for the different stages for the operation of existing up and existing down main. As you understand, as you can see, detailed staging, track and trackbed cross-sections drawings were produced in collaboration, so trackbed team with P-Way team of Arcadis, to provide clarity to the contractor for the various construction stages. Here you can see as well significant amount of ballast put on top of the permanent design here to operate the temporary operation of these two lines. The risks and constructability of each scenario or each case, such as the areas of huge excavation next to operating running lines, was particularly mitigated and discussed in detail with the client, the contractor, and Eastern's capital delivery track discipline engineers. And finally, you can see some photos of the construction. So as I said, this belongs to the capital delivery Eastern major projects and programs. The Christmas 23 blockade was completed, where mainline railway was rerouted onto a new alignment, and this is now freed up space to allow completion of construction for the new Beaulieu Park Station. And now currently in 24, the next phase of construction was partially, I think it's completed. This includes the removal of old mainline track and install foundations for the overhead mast, install cable routes and the track crossings, and building as well the new island platform. And the project is about to be completed, and I think all line now should be operational, and the station is to be open in 2025. Here you can see as well some photos of the widening area, of the embankment widening area, and here of the station. Here you can see as well some track formation construction photos from the down main and loop line areas, where you can see excavation of materials and ballast compaction. Here as well are some photos from the installation of geocell layers, the infill material laying, and the geotextiles laying, and the ballast compaction through the triple wagger. And yeah, here as well, it's track component installation from the points 5003AB. This is all taken from other LinkedIn companies, the contractors. And this is proposed. And this is some photos of how maybe the new station will look like. This is all. Thank you very much. Any questions?
Thanks very much, Maria. I'm just looking in the chat now. Yeah, it's been a bit of dialogue between Jason and Dave Brooks on. So, the first question is, how does this compare in financial saving with and without GSLs? And related to that, the potential, the additional time it takes to construct.
The financial comparison was not part of my deliverables. However, I can imagine that there must be significant savings, because we are saving approximately at least 0.2 meters along 4 kilometers of both excavation and additional broad of additional granular fill. Yeah, more information maybe I can give in another presentation about financial parameters of materials.
I had a question from myself. I saw you said in the temporary works that you installed additional ballast and then that was then removed. Does that create any complications when you have to remove the ballast above the geocels?
No, especially particularly that the new temporary alignment will be in operation, so a significant amount of compaction will happen as well for all the trackbed layers. So the removal should not interfere with it, because the underlying layers should be well compacted after the passing of some cycles of loading over more than a year, I think, or over a year at least. And I in the as well in most of the areas, the temporary location does not interfere with the permanent. Only in some areas the temporary is as well above the permanent. This was limited. The majority, the permanent, maybe only one line left was remaining, or part of the main permanent line was below the temporary line. In some of the areas, the temporary was just, where the existing up main and down main is.
Okay, thank you. Another question, can you tell us the type of geocels you've used and the brand, and you mentioned the product is improved by Network Rail?
Yes, regarding, I gave the preferred as per Network Rail standards, and I'm hoping that the contractor has installed the one specified in the design deliverable. So the product approved, from what I know, there is only one currently supplier that is approved by Network Rail. I don't know if I can reveal the name as well, is Presto's GSLs, but I know that this can be sub-supplied by maybe other UK geosynthetic suppliers in UK. And here there some 2 or 3 different depths were applied in the various sections and areas according to the requirements for the dynamic slipper support stiffness. So we used the basic one is a 200 millimeter deep or 150 GSL thickness, and other depths are applicable as well. And these all can be found in the product approval document as well of the GSLs in Network Rail. And as well, there is as well the GSL guide from Network Rail that you can use. Sorry, what else is it? The depth. So the type is defined by the specification. So once you see the product approved thicknesses of geocells, you can see the relevant properties of the panel itself, like the width and lengths of panels available. And as well, there may be the supplier may be in collaboration with the contractor who knows better the quantities and the lengths required, can maybe do alteration as opposed to the lengths and widths if required prior of this going on site. I think all this can be established between the contractor and the supplier of the geosynthetic.
Okay, thank you. And a follow-up question, how do you control the differential settlement between new embankments and existing, especially if the S&C straddles that interface?
Embankment and S&C. So differential settlement, I mean, it's not between embankment and S&C, may be on the embankment, or I think
between new and existing, I think. So
yeah,
if you've got S&C that straddles new and existing.
Yeah. So for this project, of course, each area, or whether this is plain line or S&C area, needs to be designed according to the Network Rail standards. It needs to be designed to fit targeted K values, stiffness values. So the design, first of all, for our areas are designed to meet the designed K value, so to meet the expected dynamic deflection and the expected long-term deflection. So where there is, so most of the S&Cs here are realigned. So there were not a lot of areas in this project that the existing S&Cs remained as they were. So the whole section of the SNC is looked by the designer, and so the majority of the SNCs here are almost like a new construction because they either have increase of tonnage, so the trackbed layer needs to be redesigned and rechecked to serve the expected and proposed tonnage and speed increases, and as well the plain line as well, that maybe in the majority in this project was in greenfield area, so no existing footprint. So there were not, I would say there was not a lot of areas in this project that there was difference in settlement between existing design and new construction, apart from the tie-in and the typical mitigation measures for tie-in purposes are used there, because there is a certain length of track that goes smoothly from new construction maybe to only ballast renewing, and then to scheme dig, and then to existing design. But as I said, in the embankment now, between embankment areas and cuttings, the detailed ground models and as well for the embankment settlement analysis was conducted to predict the predicted settlement in long term. And all this was checked by both trackbed and geotechnical disciplines to make sure that they will meet the requirements set in standards.
Okay. Yeah, next question. How is the stability of the height of ballast maintained in the temporary straits with traffic running?
Yeah, this was a special item that we stayed a little and we looked it in detail, and as well there was a lot of mitigation measures set, either using some like small retaining structures for that, or even the use of ballast gluing in some areas to maintain the stability of the existing running lines while excavating adjacent. And this was all provided, and all mitigation measures were provided to the contractor. Uh, in uh, in real world, I'm not 100% sure that ballast gluing was ultimately used. Pot records and Murphy and Sons, if they're here, we maybe answer that better. But yeah, I think this was provided to the contractor as a mitigation measure, the use of ballast gluing, if there was, and of course track monitoring. So I think this was what was done ultimately, and in case of any sudden track monitoring results, then the works would stop immediately.
And you mentioned formation testing for support stiffness verification. What form of testing was used, and was it different between existing and greenfield? Also, did you do any advanced stiffness testing of the existing alignments? Was the track alignment change too great?
For the formation testing, it's the specification includes the state plate load testing or lightweight deflectometer testing. So these were the specification of how these tests can be conducted was provided to the contractor and the client. And I don't have the results of all, but as well, this is now on the responsibility of the contractor to be undertaken to do it. And there was a second scale phase of the question. Was the difference between?
Sorry, did you do any advanced stiffness testing of the existing alignments?
No, it was not required. So both the shallow and deep ground investigation provided quite valuable information. So any particular stiffness or deflection measurements are specific other than just it's the automatic ballast samples, the trial holes, and deep ground investigation with the equivalent geotechnical testing on site and in lab.
And a final question, what's the calculated acceptable range of predicted settlements over the first few weeks and then the lifetime of the asset?
The expected settlement is as set by the construction tolerances between these are as set in the manual as well. And in long term, the expected settlement is less than between 5 and 10 millimeters.
And what monitoring is proposed to check the settlement values?
Monitoring was set by the PWA team. But this includes the as usual, nothing unusual, I suppose. So the usual monitoring equipment, not stiffness measurement equipment. It's level measurements.
Okay. That's all the questions we've got in the chat at the moment. Additional question: if you're laying out these GS cells and you're doing it in phases, what detail do you use where you're effectively expanding the width of the GS cell? Is there a special detail to make sure that there's no gaps forming?
Yeah, actually, these all are detailed in the network rail guidance for the installation of GSLs. And this includes specific ATRA keys to connect one panel to the other or to connect in the two edges of the GSL anything, the two different panels, and also some stretching bars when laying the geocell before the granular fill, so to stretch the panel itself, the geosynthetic panel, and then pour the infill material.
We've got a hand raised. Do you want to come off mute and ask your question?
Yeah, hi. I'm just curious to know that similar to the previous question that David asked, if we're doing the compaction of the infill material and the ballast over it over the geocell in phases, what's the height of the GSL again? Is it 100 mm?
0.2 meters.
Right. Okay. So if we are doing the infill material for the first phase within the geocell, how do we compact within geocell, and how do we compact above the geocell? What's the procedure for that?
I don't think this requires a very specific procedure. This is as well stated in the GSL's guide for installation from network rail. And from what I know, there is no like very specific machinery. It's, I think, usual machinery for compaction of the typical trackbed layers. And yeah, the compaction, that's why if you had more increased depth of geocell, that you wouldn't compact all together, because this depth is as well the depth that is recommended for a typical granular material thickness. And then you just allow 50 millimeter on top, at least some more quantity of granular material, so you will not ruin the geosynthetic itself.
Yeah.
So you compact only after you put a little more. So when you the people who operate the compaction machinery and they measure, I assume, and they get the results, they have to calculate that they will compact until they reach the top of the GSL, so they don't over compact and ruin the GSL panel. That's why we recommend ordering infill material more than just the depth.
Yeah, so
it's recommended
required
50 millimeter more.
Okay, so it's required that the height of the GSL does not get hampered due to compaction.
Yeah, do not to be
Right.
ruined.
Yeah, thank you.
Right, many thanks. Is there any more questions? I think we've gone through all the ones in the chat currently. So laptop's about to die, better plug it in. Okay, we've been okay. Thanks very much, Maria. It's been a really fascinating presentation. I've been very interested here, Aaron. Really interested in understanding how the GSL is used and how that can improve and well optimize the formation. I'm particularly going through all those details, how it's used in temporary situations and all the the details on the testing. So thanks very much. If everyone can, as they are doing, thank you in the usual manner.
You're welcome. Thank you very much for attending.